Hello, everyone. Welcome to the HPL seminar. I am very pleased to introduce our speaker, Dr. Ifaz Haider. Ifaz did his undergraduate at Carleton University in aerospace engineering, and he received a bachelor's degree in 2011. Then he started research as a graduate student at the same university and took fast track to the PhD program under the supervision of Dr. Hans-Peter Frey and Dr. John Goldak. During his PhD, Ifaz primarily investigated how stumbling loads affect femoral fracture risk using a novel gradient-enhanced quasi-brittle finite element model, and he received a PhD degree in 2016. Then he came here to the University of Calgary as a postdoc, working with Dr. Brent Edwards, and he's been working on understanding how and why people get fatigue-like bone failure. Last year, Ifaz contributed to writing an invited book chapter about bone loss after spinal cord injury, and he mentions that this experience has become one of the scientific accomplishments that he's most proud of. Aside from academic career, he also mentions that he actually wanted to be an artist because he was really into art as a kid and was actually good at it. But now he's in engineering, which is a bit different from art, but he's been using his talent for drawing a nice looking, perfect femur and tibia on a whiteboard. Today, Ifaz will be giving a talk entitled Mechanical Fatigue of Whole Rabbit Tibiae under Combined Compression Torsional Loadings is better explained by strain volume than peak strain magnitude. Whenever you're ready.
Awesome, thank you very much, Sungwon. So I'll jump right in. And actually, there, maybe that's better so you can see the whole screen. So the work I'm going to talk about today is really motivated by our group's desire to better understand how stress fractures happen in bone. And these are a type of mechanical fatigue phenomenon. So before we really get into more details, I think I'd like to take a second and kind of review what that means, just so that we're all starting on the same page. Mechanical fatigue is something that happens when a structure, such as, for example, the tibia, experiences repetitive submaximal loading. For example, this might happen when a person is running. During each step, the tibia experiences a load, but that load is certainly not strong enough to cause the bone to break right away. However, that doesn't necessarily mean that nothing is happening to the bone material. In fact, as the number of cycles increase, if we look closely at the bone microstructure, we'll see that there are some effects in the form of microdamage. Here on the screen, I'm showing one type of microdamage, which are these linear microcracks that are known to form in and around the osteons of cortical bone. Now, if this person continued to do this type of loading too much, too fast, in a way that overwhelmed their body's ability to naturally repair, this would eventually cause the microdamage to accumulate, resulting in lowered bone material properties. And if they kept going, eventually this would lead to a fatigue failure, or what we call stress fracture. So this phenomenon of fatigue failure in bone is something that's really well studied at the material level. By that, what I mean is researchers will often take a big whole bone and cut out a tiny little sample from it, maybe just a few millimeters in length. And then they'll load that material sample on a machine to see how the bone behaves. One very important study of this type was done by Carter et al., who showed how changing load, in this case expressed as strain, influences the number of cycles to failure. And that's the data that I'm showing on the screen right here. So as you can see, there's a very clear relationship between the applied load or strain and how long the specimen survives. And if you look at this graph, you might be tempted to think that it's a really nice linear relationship, but you'd actually be a little bit wrong, because I want to draw your attention to this scale over here. In this graph, cycles to failure is plotted on a logarithmic scale, which means that there's a very highly nonlinear relationship between loading and the number of cycles to failure. It means that small changes in load have a big impact in terms of fatigue life of bone specimens. Of course, a test like this is maybe just a little bit too simple to describe exactly what's happening in real bones during more realistic loading. In fact, there's been a lot of in vivo measurement work involving both strain gauges and bone pins that suggest that during realistic loading, the bone experiences a combination of axial and torsional loading. And with that in mind, another group, Vishithi et al., decided to look at combined biaxial loading. And they got sort of similar results. By that, what I mean is, actually, let's stop and let me show you how to read this data that I'm showing on the screen. On the x-axis, the number indicates what percentage of strength, and the letter indicates what loading mode. So a 25A 50T specimen was subject to 25% of the axial load and 50% of the torsional load. And so from their data, we see a couple of interesting features. First, they noted that if they held the axial load constant, but added progressively increasing torsion, they again got this nice nonlinear relationship. Again, it's nonlinear because this scale is logarithmic between increasing torsion and the number of cycles to failure. The other cool thing they found is that comparing the 25A condition to the 25T condition, it appears that bone is particularly sensitive to failure in torsion. So these are really interesting studies, and there are many more like it in the literature. But at the end of the day, we're not really super interested in necessarily how tiny pieces of bone behave. The reason why we do work like this is because there's this assumption that understanding this scale helps us infer what's happening to larger whole bones. And that's certainly true to an extent, but that translation from small materials to big whole bones is something that's not necessarily all that straightforward. And I want to talk about a couple of reasons why. The first is because there's this notion that fatigue life of a specimen depends on specimen volume. And I think one of the best studies that shows this in bone was done by Bigley et al. So what they did was they took horse cortical bone and they machined specimens that were largely identical to each other, except some were longer and some were shorter. As a result, when they went and did fatigue loading to a fixed strain level, they were able to get specimens that had large strain volumes versus ones that had small strain volumes, while keeping everything else about the test more or less constant. And what they found in this data was that, as you can see, there is most certainly a dependence on fatigue life in terms of the volume of the specimen. Bigger volumes had a tendency to fail sooner than small samples. And this is something that's actually really well documented in literature. It's not unique to bone. In fact, it's been observed in lots of other engineering materials. And I've seen references to this behavior, going as far back as the 1920s. And in general, the explanation for why it exists is always the same. Researchers say that there's a probabilistic nature to crack nucleation and growth near microstructural weak points, which is, that's maybe a bit of a confusing statement. So let's kind of bring that back down to the context of bone and biomechanics. So for example, in bone, we might say that the existing microcracks in the bone, the ones that have occurred just as a part of daily living, might wind up being microstructural weaknesses that result in overall failure. If that's the case, let's look at how that changes across different scales. Well, in general, research seems to suggest that in bone, we see a crack density of about 0.022 to 2.9 cracks per millimeter cubed. And that would mean that if we're testing a small sample somewhere between 50 to 150 millimeters cubed, we might see only about 11 cracks in this small sample. However, if we were to look at the entirety of the bone, which is definitely a lot bigger than this volume, maybe we'd have much, much more. We might have up to about 2,000 cracks in the entire bone. And this is where originally I struggled to think of a way to sort of easily describe why 2,000 cracks might be worse than 11 cracks. And I really like the analogy that Brent uses, which is we're basically looking for the weakest link in the chain. And when you have 2,000 cracks in your specimen, there's just a greater probability that one of them is particularly bad and causes the whole thing to fail. So ultimately, that's why we believe larger specimens fail sooner than small ones. So that's the stress volume effect. There's another thing that makes it a little bit difficult to infer between the material level and whole bone level. And that's this idea of stress and strain non-uniformity. And let me show you exactly what I mean by that. When we do material level testing, we intentionally machine fairly simple shapes out of the bone, and we subject these shapes to relatively simple loads. And as a result, we get very uniform distributions of stress and strain. However, this little piece of bone that we run our experiment on is meant to represent only a tiny piece of the more complex whole bone. And that whole bone has both very irregular geometry and heterogeneous material properties. And so it's not surprising when we see that under even equivalent or very similar loading conditions, we get much more non-uniform, much weirder patterns of stress and strain on these bones. And when we combine what we know from the previous few slides, this means that we think that the fatigue failure at this scale really depends on both the magnitude of these strains as well as the size of these elevated strain regions. And so hopefully at this point, I've kind of convinced you why it can be a little bit challenging to go from understanding the small bone scale to understanding how whole bones behave in terms of fatigue. So how do we study something like that? Well, our group uses two different tools predominantly, and I want to talk a little bit about what those are. So one of the things that we often do is we run ex vivo experiments. This basically involves taking a bone, either an animal sample or a cadaveric one, and putting it into a material testing machine in order to literally observe how it behaves under fatigue. This is a really great technique because it tells us a lot about when and how a bone might fail, but it also has some key limitations. There's two in particular that come to my mind. The first is that it's very challenging to assess the stress and strain distributions throughout this bone during a test like this, and that makes it hard to relate what we're seeing back to what we know about bone material. The other problem, of course, is the fact that because this type of testing is very invasive and destructive, it's not something that can really be used directly in a clinical setting. So in order to overcome some of these challenges, our group likes to sort of augment our mechanical testing with computer simulation and finite element models. These are models that are specimen specific. They're basically based on medical imaging of the actual bone itself, and it provides us a way of simulating the mechanical response to loading. That means that we get predictions of the stress and strain as they occur throughout the model. And one of the great things about that is this whole technique is completely non-invasive, which means that it can be very easily adopted for clinical use later on. So that's kind of a bit of background information on what and why we do, but let me get into a bit more detail about what this study really is all about. So the purpose of the study I'm going to talk about today was to examine the organ level fatigue failure of bone using a rabbit tibia model. And in this case, we chose specifically to use a rabbit model because rabbits are one of the smallest mammals that exhibit intercortical remodeling. So that means that the rabbit has a bone microarchitecture that's very similar in a lot of ways to what we'd expect to see in humans. And so we think that the data are relatively easily translatable, making this a good model. In this study specifically, we had two different elements, two different tasks. We had an experimental portion where we quantified the relationship between load and fatigue life under both uniaxial and biaxial loading conditions. And then we did some finite element modeling where we were trying to develop models that help us predict the behavior that we observed during our experiment. So over the rest of my talk, I'm going to kind of separate it into two parts. First, I'll talk a little bit about the experimental side and what we saw from that. And then I'll talk about the finite element models that were made based on these experiments. So jumping right in, as I mentioned, in this study, we were using a rabbit model. It was a secondary use protocol. So we had female rabbits aged between 8 to 16 months old. After the rabbits were sacrificed, we harvested the tibia and they were put into a CT scanner. This would form the basis of our computer simulations to come. But for now, we skipped ahead. And after scanning, we potted the bones in PMMA and loaded them onto a material testing machine. At this stage, we sort of split up our specimens into one of three different types of experiments that we ran. the first thing we did was we took a few of our bones and we used them to categorize the ultimate force and the ultimate torque, basically what it takes to break the bone just in monotonic conditions. And this really gives us a basis for figuring out appropriate loading to use during our fatigue loading protocols. Speaking of which, the first fatigue loading protocol that we did was simple cyclic compression. And we did this across a range of different peak forces. So we had specimens going from up to 925 to 2450 newtons. Now, keeping in mind that our ultimate force test showed that these bones break at approximately 2,500 newtons, this meant that we got a nice wide range of time to failure across these 12 specimens. After the uniaxial compression test, we also looked at biaxial loading. Here we took our remaining bones and we separated them out into 3 groups. And again, I know these numbers can look a little confusing, so let me describe in detail exactly what they mean. The first number indicates what percentage of the ultimate force they experienced during the peak of loading, and the second number indicates what percentage of the ultimate torque they experienced. So a 50-25 group animal during the peak of loading experienced 50% of its ultimate force in compression and 25% of its ultimate torque in torsion. So that's kind of a brief summary of all of our mechanical tests. Let me show you what we found. In general, we observed, as we expected, a very nonlinear relationship between load and fatigue life. So this is kind of what that looked like in the uniaxial compression case. And as you can see here, I'm plotting the peak load on the x-axis and the number of cycles to failure on a logarithmic scale on the y. And our data was really well described with a power law type relationship, very similar to what's been done in the past for bone. We got a similar result when we looked at the biaxial loading tests. Here, again, what we have is a situation where axial loading is held constant, but torsion is increased progressively. And again, we see a nice nonlinear decrease in the number of cycles to failure as we superimposed more and more torsion. Though when we did statistics on the groups, difference really only became statistically significant when we looked at our 2 sort of most extreme cases. Before I move on, there's one other feature from these data that I really want to draw your eye to, and that's just how much spread there is in data like this. And to really highlight that, I want to draw your eye to the 50-25 case. Now, these are all bones that experienced exactly the same loading, and yet some of them failed at less than 1,000 cycles. Some of them went over 100,000 cycles. And this was not surprising because ultimately, this is sort of what we expected to happen, because remember, at this stage, all we're doing is we're looking at what load is applied without any notion of just how strong or what the structure of these individual bones look like. And that's really what the second part of the study was all about. It was saying, can we add some information about the structure of these bones to explain why some fail quickly and some don't under the same loading? So it's been a while since I talked about that second part of the study, so let me just kind of reiterate exactly what we were doing. In this study, we were developing finite element models in order to predict the observed fatigue life behavior that we got, and we did that based on the simulated patterns of stress and strain. Of course, our hypothesis was that by looking at stresses and strains in these different bones, it would help explain the variation that we see in the experiments. So before I talk about exactly what we found in this phase, now's probably a good time to go over exactly what goes into making a subject-specific or a specimen-specific finite element model. Of course, it starts with those CT images of the tibia that we took prior to mechanical testing. The first step is to do what's called segmentation, which just involves automatically or semi-automatically figuring out what's bone and what's background. After we have that volume, we do a process that's called discretization. Basically, we take the volume and we break it up into little tiny regular geometric pieces called elements. As the name suggests, these elements are a really crucial part of how the finite element method works. And in this talk, I don't want to get into necessarily too much detail about exactly the mathematical specifics of the finite element method, but I think a general overview might be helpful. basically, because this is a nice regular geometry, we're able to use principles of continuum mechanics in order to describe how applied forces cause deformations of each individual element. And we can do that for every element in the model. We then know that all of these elements in the model are not independent of one another, but they're related by the fact that they share nodes and edges. And so we can take this information and put it all into one big matrix that we solve in order to figure out exactly how the structure as a whole responds to different types of loading. But I'm getting a little ahead of myself here because after we discretized the mesh, there was still one important step to do, which was we assigned material properties to our model. In our case, we used heterogeneous material properties that were based on local CT measurements. And you can kind of see the reason why that might be necessary when you kind of focus on this cross-section of the tibia that I'm showing here. As you can see, some parts of the image are very bright, indicating that the bone probably has a lot of density. It's probably very stiff over there. There are other parts of the image where it's not very bright, it's a lot more dim. And that would seem to suggest that there's less dense bone in that region. And so we expect that bone to have a lower Young's modulus. And in all of our scans, we had an object that was called a calibration phantom. This is basically just a region with known mineral densities at 3 of its sites. And so by measuring the calibration phantom, we're actually able to sort of quantitatively relate the CT measurement, or the brightness of this image as I'm showing it here, to an actual bone density value. And this bone density value kind of forms the basis for how we might estimate something like the bone's Young's modulus. Now, in the literature, there's a very well-established relationship between bone density and Young's modulus. And it's usually described with an equation that's kind of like this, where the Young's modulus is equal to some constant A times the density raised to some power B. The tricky part is figuring out exactly what A or B should be for a given set of models. And you can kind of see why if you pay attention to this data that I'm showing on the right, which was done by Morgan et al. Here, they basically tried to quantify the density modulus relationship using all human bone just from different sites of the body. And as you can kind of see from this graph, they get a different relationship depending on where on the body they actually took their specimens from. Of course, in our case, we have to contend not only with that, but the fact that we're talking about rabbits and not humans. And we certainly weren't able to find data that looks like this for a rabbit tibia. So we did kind of the next best thing, and we estimated A and B based on some experiments. Specifically, we took a few of our tibia and put strain gauges onto them and measured strains during loading. We then used Nelder-Mead optimization in order to find the parameters A and B that sort of maximize the agreement between the finite element model and the measurement that we took. And as a result, we got an equation that looks something like this. And we were actually rather pleased with where we ended up because the exponent that we got made a lot of sense. An exponent of 1.5 is, very much within the range of what's been reported in other bone in the literature. And overall, this relationship seemed to yield Young's moduli of bone that made sense when we put in sort of approximate densities of cortical rabbit bone. So in general, this seemed like a really good starting point for this study. So after the material property assignment, we were able to move on to kind of the last step in finite element modeling, which was we took the subject-specific models of each bone, and then we applied loads and boundary conditions that mimicked exactly the mechanical test that I talked about earlier. As a result, as an output from these models, we get a distribution of stress and strain that basically represents our best prediction of how this bone is responding to those loads during the experiment. Now, in this study, the last step was to take this sort of very complex data and reduce it down to a few relatively simple measures. And our goal was to find finite element measures that explain the variation in our data. Another way of saying that was when we plot the cycles to failure against some of these FE measures, we're looking for the ones that give us really good R-squared values. Now, at this stage, we had some ideas that about what measures we should be using, that some things would work really well and other things wouldn't. And this was all sort of based on what we knew from the material science. And also what we knew based on kind of our previous experience doing failure modeling under monotonic conditions of whole bone. However, we did note that in the literature, people really haven't explored this issue at all in the context of whole bone fatigue. So we actually looked at a number of different measures in order to demonstrate what works and what doesn't, and basically see if our ideas were correct. With that in mind, specifically, we looked at 3 different phenomena. We looked at the idea of stress versus strain, we looked at peak versus strain volume, and we looked at different failure criteria. So I'm going to take a bit of time and talk about exactly what each of these 3 things are and why we looked at them. So first, let's talk about stress versus strain. Essentially, we can always model failure either as a function of the strain, which is the local deformation that the bone is experiencing, or stress, which is basically how much load is carried at each site. Both are sensible, but material science and sort of material level testing suggests that strain-based measures are probably more robust, because it seems that the strength of bone changes a lot with its density, and yet regardless of density, bone has a tendency to fail at a very similar strain. And so we used both conditions, and we wanted to see which one would work better in fatigue. The next thing we looked at was this idea of peak versus strained volume. And this is because in the literature, from what we saw, peak strain is really what's most commonly used in fracture assessment. But we suspected that this might not be a great measure because it doesn't necessarily account for size effects. And I think a great example is this one really extreme example from one of our tibia. As you can see, the peak strain is really just happening over a few elements in the tib-fib junction. And yet, when we look at the rest of the body, there's sort of sites of high strain all throughout. We suspected that a measurement of peak strain doesn't necessarily account for what's happening elsewhere. And what's happening elsewhere probably has some effect on the fatigue life, given what we know about size effects. So in this study, what we did was we decided to use both peak strain and strained or stressed volume measures. That is, we counted the volume of elements that were above a certain threshold. The last thing that we wanted to explore in this study is this idea of failure criterion. And this was really sort of motivated by that data by Vashithi et al. That I was showing you guys earlier. Remember, when they did a load to 25% of the axial load versus 25% of the torsional load, their data seemed to suggest that bone was particularly sensitive to torsional failure, even when you account for the fact that there's relative differences in monotonic strength. So we thought that this is a phenomenon that we probably could incorporate into our models if we picked the appropriate failure criteria. And so in this study, we decided to explore 3 different failure criteria and see which one worked best. The first thing that we looked at was this idea of max versus minimum principal strain. And this is a criteria that works really well in the past for brittle materials. And it basically just means the way this works is you look at the deforming material and you try to find the direction in which it's stretching the most or it stretches the most negative. Those are the max and minimum principal strains. Another criteria that we looked at was the von Mises criteria, which is something that works quite well for ductile materials, but has also seen a lot of use in bone. This criteria, basically what it says is that it separates out the deformation into a hydrostatic or a volume changing and a deviatoric or a shape changing component. And it says that failure is based on the energy associated with the shape changing component of the deformation. The final thing we looked at is this slightly more fancy criteria called the pressure modified von Mises criteria, which in the past has been used quite successfully with all sorts of quasi-brittle materials that exhibit strength asymmetry. And specifically, I decided to use it here because in my thesis, I found it worked really well to predict the failure of at the hip. Basically, what this criteria says is, it says that, you know what, the volume changing and the shape changing components of the deformation probably both relate to failure, but just in different proportion. So that's kind of everything that we were trying to look at. Just as a reminder, basically what we were doing was we were picking some finite element outputs, and then we compared them to the measured fatigue life, and our goal was to find the ones that really had good R-squared values. And so for the next couple slides, I want to show you some of our results. I think the way I'll do it is I'll start by showing kind of in detail a few of our regression relationships, the ones that really highlight some of the key findings from this study. But then to speed things along, I'll just show you the rest of our data in tabular form. So jumping right in, one of the very interesting things we found was that in the uniaxial loading condition, both peak strain and strain volume were reasonable predictors of failure. And that's kind of what I'm showing here. So on the y-axis, again, I'm plotting the cycles to failure on a logarithmic scale. On the left-hand side, the x-axis shows the peak pressure modified von Mises strain. And on the right-hand graph, it's the volume where the pressure modified von Mises strain exceeds a specific threshold. And as you can see, though the volume-based condition did work a little bit better than the peak strain, the peak condition still wasn't really bad. It still generally explained our data quite well. This is under uniaxial compression. However, we saw a completely different situation when we looked at our biaxial test results. Here, peak strain basically did almost nothing for us. It didn't explain any of the variation that we were seeing. And yet the strained volume criteria turned out to be relatively robust. It continued to explain the variation that we were seeing in the biaxial loading case as well. So that's one key finding from all of our simulations. Now I want to show you everything else that we were able to kind of identify from our data. And to do that, I'll walk you through one of the tables from our publication. And I know it's certainly a bit of a pain to try and interpret or read a table in the middle of a presentation. So I promise I'll go slowly and I'll spend a little bit of time and I'll really draw your eye to the parts that matter. So first, let me show you how we're going to read this table. In the columns are some of our different measures. Sigma indicates stress, while epsilon indicates strain. We looked at the von Mises, maximum principal, and minimum principal criteria, as well as the pressure modified von Mises strain. In the rows, I'm going to show you the R-squared values associated with the peak of the measure, as well as strained volume measurements using one of 3 different threshold values. Finally, I'm going to show you the results for both the uniaxial compression case, as well as the biaxial loading case. So here's some of the things that we identified when we looked at our tabular data. One of the things we noted was that, as we sort of hypothesized earlier, strain-based measures generally did better than their equivalent stress-based measures. And I think that becomes most obvious when you look at maximum principal strain versus maximum principal stress. Clearly, the R-squared values for the strain measure are just much, much higher in this case. Another thing that we found is when we looked at different failure criteria, it seemed that both the pressure modified von Mises strain and the maximum principal strain were equally good and equally robust. And that becomes, I think, most evident if I draw your eye to the biaxial loading case, which was really, it seemed to be the most challenging one to predict. And again, both of these failure criteria did reasonably well at predicting this situation. I already talked about the fact that strained volume generally worked better than peak strain. But another thing that we did identify in this study was that because before we didn't really know what an appropriate cutoff for strain volume would be, our data here seemed to suggest that 3,000 or 4,000 microstrain were sensible cutoff values. So that's all the data that I wanted to show you today. And I know it was a whole lot, so let me take a second and kind of review exactly everything I talked about, and more importantly, what that means to us as biomechanists. So the first thing we noted in the study was that when we're looking at the whole bone level in rabbit tibia, we certainly saw a very nonlinear relationship between the applied load and the cycles to failure in a way that really is consistent with what we expected based on material studies. And this is a very important result, especially as biomechanists who maybe don't always want to run a finite element model. And it's a very encouraging result, I think. It means that if we're trying to find ways of helping people, we only need to make subtle improvements to the loads that their bones experience, in order to get big impacts in terms of fatigue life. Another very important thing, however, that I want to point out is that I think we do need to be very cautious about looking at load alone. And this was particularly evident when we looked at our biaxial testing case, which I think was really the more physiologically relevant of the two types of tests, because this case in particular really seemed to reveal the fact that there's a lot of variability in fatigue life that load alone doesn't explain. And of course, in this study, what we were able to demonstrate was that it seems that, yes, the mechanics of the bone really do play an important role. Here, that was something that we assessed using finite element models. And at the end of the day, yes, our finite element models did help explain a lot of this variation. But there's one thing I do want to kind of emphasize caution about, which is the fact that we do need to be careful to look at correct model parameters. In this study, we didn't use anything that we thought was nonsense. Every sort of measure that we evaluated has something that had some sort of physical basis, and yet some of them worked quite well, but others really didn't work well at all. And so I really wanted to emphasize this fact and kind of reiterate the importance of doing sort of validation experiments like this in order to figure out exactly what we should be pulling out of our finite element models. With that said, our overall conclusion is that strained volume based on pressure modified von Mises or maximum principal strain are what ultimately best explained our data. And there's a whole lot in here, so let me kind of break down exactly what each of these pieces mean and what they tell us. First, it was strain that worked, not stress. And this is really something that we expected based on material level studies. Ultimately, stress is very sensitive to changes in density between specimens, whereas strain is much more stable. So we're not surprised that overall a strain-based criteria is what seemed to work best. It was also strained volume, not peak strain, that seemed to be a very robust measure of fatigue life. And again, that really does match with what we expected based on what we know about the importance of stressed and strained volume. Finally, the last thing I want to draw your attention to is which failure criteria ultimately worked. We found the pressure modified von Mises and the maximum principal strain criteria worked really well. These two criteria ultimately in the past have worked really well with brittle or quasi-brittle materials that are exhibiting sort of a tensile failure mode. And so we think that's exactly what's happening here. At the end of the day, the thing I want to leave you with is the fact that it was really cool in this study that we did see pretty strong R-squared values between our finite element models and our measured fatigue life values. And this means that we have some faith that a model like this could stratify human bones by who's strong and who's weak. And something like that could have a lot of clinical utility. However, that is a very important next step for work like this. I think it's really important that we sort of try and apply these techniques to human bones in order to make sure that these measures really do relate to clinically important outcomes. So that is everything I wanted to talk about. Thank you so much for your attention. I know I skimmed over a lot of things very quickly. If any of you guys are interested in learning about this in a lot more detail, we recently published these results in the Journal of Biomechanics. And then I'd like to thank my PI, my co-authors, and the rest of our lab group and funding sources. And on that note, I'll kind of open things up and take questions.
Thank you very much, Ifaz. I really enjoyed your talk. So before we get to the discussion, I would like to kindly encourage everyone to turn on your camera during the discussion period, so we see each other have a active discussion. Thank you for doing that. So if you have any questions for our speaker, Ifaz, please use the icon raise hand button. You can find it under reaction icon at the bottom of your Zoom screen. Also, if your Zoom version is different and you can find the button there, please also feel free to send me a message via Zoom chat. Then I'll call on you when it's your turn. Now I'll open the seminar to the questions. Actually, let me start asking questions first. So I do have a couple of questions. So when you were, so you had like in your experiment part, you had 3 different loading conditions. And then first I wanted to ask you if the loadings, how are they comparable to the relative to the daily movement? So like you applied the loading to the in vitro testing, but I'm just curious how similar would that be in real life?
Okay, so in terms of the biaxial test, in terms of getting the proportions of compressive load to torsional load, the authors that did the biaxial test at the material level, what they did afterwards was they broke down the ratio of maximum principal stresses and strains to the ratio of resolved shear or resolved torsion. And they sort of evaluated what these various combinations did with respect to what's observed in strain gauge testing in humans. And they said, yeah, these proportions of load are certainly very relevant. In terms of actual loading magnitude, well, I can say for a fact that our rabbit bones definitely were loaded to much less force than I think a human bone experiences. But in terms of cycles to failure, I'd suspect that maybe we terminated our study around, as an upper limit, we picked 500,000 cycles. And maybe that's a little bit low compared to how many cycles it takes in humans, so I'm really not 100% certain on that. But I would suspect that maybe we're loading them a little bit faster, if I were to speculate, than what a human bone might fail at realistically. But not by much. Hundreds of thousands of cycles are still a lot.
Yeah.
I figured Sung-Wan was asking about how the loads related to the loads a rabbit experiences.
Oh, on that note, I don't have.
Is that right? Is that right? Is that what you were asking?
Yeah, I'm just curious, like not relatively to the rabbit's movement, but I just curious like how the loading itself is related to our daily movement in human, just like.
Oh, okay. All right.
Yeah.
Yeah.
So I'd say in an order of magnitude sense, we were trying to get, times to failure that are relevant for human. I certainly don't know exactly what the loads on a rabbit tibia are, but because we're trying to say something about humans, we didn't really pay too much attention to what happens to the rabbit in nature.
I see. Thanks so much, Ifaz. Even though my question was not clear.
No, it was.
I see, Rob, you have a question for Ifaz?
Well, just following up on your questions, Xiongwan. When I see these repetitive strain studies done on bone, it's always sinusoidal. And I wonder if you change the duty cycle to be more what a bone experiences, which is nothing at all, and then a strain, then nothing at all and strain. So just have I don't know what it'd be, would it be a 25% duty cycle, whether the bone would get a little rest period, little recovery period between each one, or whether it would make no difference. I'm just wondering if you had a comment on that.
Sure. So in engineering materials in general, there's this principle called Miner's rule that's used to estimate how things behave under different duty cycles. And so the general result of those, if I'm remembering right, is that the rest period in typical engineering materials doesn't really help it. So doing 200,000 cycles right away is typically about the same as doing 100,000 and then resting for a little bit and doing another 100,000. That of course,
I mean between each single cycle, like when
yeah.
you run, you do a hit and then you do nothing. So it's
so
one cycle.
That principle scales. So one cycle break, should be very similar to lots all at once. And in fact, there was a really great study by Zayopos et al. They weren't doing breaks, but what they were doing was they were playing with frequency. And what they found was that it really turned out to be the overall duration of loading in bone that determined when it broke. So like you could go faster, you could go slower, as long as your total duration of loading was hit, that was when the bone would break. So I suspect something like that would be very relevant for bone. I know some people have hypothesized, well, of course, in reality, there's perhaps remodeling-based recovery, but that's not what's happening at this scale. Some people have hypothesized that if you have breaks, you can get sort of non-biological, or I'd want to say sort of material sciencey based recovery mechanisms, but that's never really been shown. So I don't really, I don't know, or I don't think that plays a role. Yeah.
Thanks, Ifaz.
No problem.
I see Emily, you have a question for Ifaz?
Hey, Ifaz, that was a very
Hello.
nice,
Thank you.
clear talk. So correct me if I'm wrong. For the model, you explored multiple failure criterion, correct?
Mhm.
And then for the physical material testing, how do you determine failure?
Oh, for our physical experiments, failure was defined as a complete rupture of the bone. So in ours, it was really clear because they usually just shattered.
Okay, so it's sort of hard for me to compare then, because for then your model experiments, some of your parameters are defining failure at a single location. Like when you're using the peak strain, that means you're predicting failure at a single location.
Yeah.
Okay.
And ultimately, that's why we suspected peak isn't great, because it doesn't take into account the fact that in reality, it's possible for a structure to sort of experience a very local failure, but still remain mostly intact. Actually, my PhD thesis was all about that phenomenon, but we didn't include that in any of these models because really, I think at that point you get something very unwieldy. So whereas something like this solves in about 15 to 20 minutes, I made a nonlinear simulation of that phenomenon in fatigue, and just with a tiny little, like very regular geometry, it was running overnight. So yeah, but that's why, among other things, we think a strained volume-based approach sort of helps with that, basically.
Cool. Awesome. Thank you.
No problem.
Scott, please go ahead.
Thanks, Ifaz. So I guess I have 3 questions.
Sure.
I have a technical question if you want that first, and then more applied questions
Yeah. Go
after
for
that.
it.
So you're modeling all the elements in your model are an isotropic material, right? I missed the beginning, but it's just Young's modulus, right? Young's. But so at the material level, the material is isotropic. But given that it's so heterogeneous throughout, I assume structurally the bone is anisotropic in its behavior. Have you considered, in addition to the yield criterions you tested, something that's an anisotropic yield criterion?
Yes.
I imagine you have.
If I was going to go back to this, I think that the next thing I would do is I would put in an anisotropic material, not just an isotropic one.
Okay.
I suspect, if anything, what that would do is that would give me even better results for the torsional condition specifically.
Right, and also the biaxial is what I was thinking as well.
That's the one I'm.
Oh, your biaxial test.
Yeah,
okay.
The biaxial test. I suspect we'd get even better results for the biaxial test if we incorporate that behavior.
Okay, and that leads into the next question. I assume from CT, isotropic like CT images, you're able to get an estimate for bone anisotropy somehow, somewhere in the signal.
Usually what you do for bone is you look at how it's oriented with respect to the long axis.
Okay, what's the long axis?
So if you have, and this is where I really miss having a board, but I don't know if you can see this, but so if that's the proximal end and that's the distal end.
Of the bone, okay.
Of the bone, yeah.
Oh, I thought it meant something with respect to the CT image.
No.
Okay.
No.
So, but there are ways of measuring anisotropy from like a clinical CT.
It's estimated. Basically, you
like correlated.
Yeah, you orient your bone along, say, the anatomical or the shaft axis, and then you say that there's one material property. It's proportional, so that's how you take into account heterogeneity. You say that the number that I use in this study that I reported with that equation, that represents the longitudinal or the on-axis Young's modulus. The other moduli would be some fraction of that.
Okay. And then the final question, so you talked about brittle versus ductile materials and how they have different failure modes. And I assume as people age, or what I've always been told is bones both lose density but also become more brittle. So I assume they lose collagen content or something that gives them the ductile properties. Is there a way to quantify that from a clinical CT or X-ray?
So I really haven't seen enough. The problem with that is when we do studies, we almost, in terms of like real specimens, we almost always get older people. And so I haven't seen enough studies, or any studies that I really think of, that do a lot of testing of very young people's bones for a point of comparison. So
could you give animals something like bisphosphonates or something and make their bones brittle?
We can give bisphosphonates to animals, and yes, stay tuned for that.
Oh, okay. All right, cool.
We're doing
All
that. I don't know if it makes their bones more brittle though, but we'll be able to tell you soon enough.
Okay. Yeah. Well, thanks.
No problem.
Art, please go ahead.
Hi, my question is about what you think the mechanisms are. And I guess the issue here is that you're looking for a measure that is predictive of when a bone is going to fail. And then and there are a bunch of measures, and I think some measures are better than others, and it depends on your imaging modality and things like that. So it's very complicated. But I'm wondering, do you have a relatively small number of failure mechanisms? Like, what I mean is, you may be finding a measure of von Mises strain or stress, but is the mechanism of failure a small number of things, like failure in tension, failure in shear, and stuff like that?
So I hope I understand what you mean by mechanism correctly, but yes, I suspect that the way I think of it is sorry, give me a second to think of a way to articulate what I mean. Ultimately, I think there is sort of one failure mode that's dominant in this type of test. If I were to guess based on our data, it seems like it's a tensile failure mode underneath the hood. That's what's happening. And I only say that because the maximum principal strain and the pressure modified von Mises strain criteria, they seem to work really, the cases when they work really well is when you're looking at a material that's undergoing a tensile failure mode. So I hope that's what you meant, and I hope that answers your question.
That's exactly what I meant. And so then what I'm curious about is, can you use the mechanism to sort of predict what combinations of measures are going to be best correlated? So basically assume that you are correct on your mechanism, and then based on the loading that you're doing, you have all these measures. I'm assuming that they are correlated in various ways, but you have a bunch of measures. Some of them are going to be correlated more with tensile loading, or and then some will be perhaps correlated more with shear or something else. And so the idea is that you have multiple measures, and there are various reasons why they're going to be good or bad. But if you're ultimately interested in mechanism, I'm wondering if you can sort of make the connection from your hypothesized mechanism through multiple measures into what you're trying to do.
Again, I hope I'm interpreting it right, but so let me know if I answered completely the wrong question. But so from the fact that, for example, a maximum principal strain criteria is what works, what that means is that it doesn't matter what type of load, or basically it's, if we're right, it means that it doesn't matter what exactly causes the maximum principal strain to be hit. So torsion causes a certain amount of principal strain, compression causes a certain amount of principal strain, and what our data seems to suggest is failure is happening when that threshold is crossed.
Okay, but if you're interested in principal strain, isn't that automatically saying that it's going to be compressive or tensile stress and not shear?
Shear also causes principal strain. So it's in a different direction though.
Oh, I see.
Yeah. So
Okay.
in fact, a very characteristic thing is when you put torsion on a big whole bone, very often we see a spiral fracture. And that's because the maximum principal strain under shear is highest at 45 degrees.
Oh, yeah, but I think of that really as, so that's a tensile failure,
Yes.
right? So yes, you're loading it on the outside in shear, but then the failure mechanism is still tensile.
And
So
that's
so
what the criteria helps you sort of identify, irregardless of what you're doing on the outside. So basically you're able to make equivalences of how much do I, if I torque it, when is it going to break versus if I squish it, when is it going to break?
Okay, so what I'm interested in is basically, I think there are only a few degrees of freedom or a few hypotheses about what the actual failure mechanism is on the inside. Say tensile failure, compressive failure, shear failure, stuff like that. And so you can have a whole bunch of measures, but I'm imagining that the measures are, they have various correlations between them. And then the question is, can you sort of take a, I don't know, kind of a multiple regression approach? So just, you know, starting from the data, what combination of measures, take your pick, any kind of combination gives you the best R squared. And then you might separately try to take those sort of groups of measures and then ask which of those are most correlated, say, with your hypothesized failure modes. Or you can build from the bottom up. Hypothesis-sized failure mode, predict how certain measures are going to be correlated with each other. And then, so the idea is that you don't have to be keyed on the R squared value for a single measure, but you can be looking at R squared values of certain combinations of measures.
So I wouldn't say that, so I agree that our, the different criteria aren't necessarily 100% independent of each other, but they are extremely sensitive to some things and not others. And in that way, they are they're not actually super correlated in the sense that, for example, a von Mises criteria is extremely sensitive to shear in a way that a maximum principal criteria is actually quite dull to shear. And so in that way, and this is kind of the approach that's generally taken when trying to figure out what works for a material, the assumption is that if you have sensible cutoff values, the cutoff that gets hit first, based on which failure criteria, probably means that its dominant mode is the one that's involved in the failure. So because in our case, it was maximum principal strain that was, you know, showing the variations between, so the ones that were failing quickly had lots of maximum principal strain, the ones that were failing less had less maximum principal strain, and we didn't see that sensitivity in other measures that didn't pick up on tension as well. That is our indication that it probably is a tensile failure mechanism.
Okay, that's exactly what the kind of thing I was hoping to see. And I don't mean to say that all your measures should be correlated with each other. What I mean is certain combinations of measures should be correlated with certain hypothesized failure modes. Yeah. And then, so let's say you have 10 measures, a 10-dimensional space is hard to deal with, but let's say you only have 3 strong candidates for hypotheses. So then out of your 10-dimensional space, I'm sort of imagining that there are only 3 sort of directions or combinations in that 10-dimensional space that might really matter. And so I'm wondering whether you can use that. And it sounds like you are already thinking that direction because you do have this hypothesis about the tensile failures.
So what the underlying 10 measures really are, and I didn't really go into this in this talk, is there are 6 strains that are acting on the specimen. That's the elements of the strain tensor. These measures are distillations that focus on important aspects of that strain tensor. So invariants of that strain tensor that are loosely, they're meant to measure different things. So in that sense, I think what you're talking about is sort of baked into the specific choice of using these distinct failure modes.
Right. Okay, great. Thank you.
Can I just jump in? So when you look at the fracture pattern in the specimens that are loaded in uniaxial compression, and they do of course bend under compression. There's a compressive surface and a tensile surface, but they're loaded in uniaxial compression. The fracture pattern is very much an oblique type of fracture pattern. So it actually looks like it's failing because of some kind of maximum shear strain. It doesn't look like it's necessarily failing because of because of a tensile failure mode. The ones loaded in high torsion, 50% ultimate strength torsion plus axial load, they very much illustrate spiral fracture pattern. So it's a tensile failure mode. And then the one that was kind of in between sort of has this intermediate, it's not a 45-degree angle, it's kind of in between. So, so we know why these things are failing. We don't have to make a hypothesis about why these things are failing. We know why they're failing. And for us, it was really about, and so it wasn't necessarily a fishing expedition. We kind of knew that the pressure modified von Mises criteria would be better because it's going to be, if the material's failing because of a maximum principal strain, because of a tensile failure, or it's failing because of a shear failure, this specific criterion should be able to handle that. And so I think that's why it did the best, and everything else was really just to sort of cover our basis, so to speak.
Oh, okay. Then I think I would suggest to make that the expectation. So then we can sort of be looking for that measure to work better than others.
You start neuromechanics up again, so Ifaz can present to you.
Yeah.
And then you can make that suggestion.
Okay.
I see, Walter, you have a question for Ifaz?
Yeah, thanks, Songwan. And Ifaz, thank you for a very clear talk that even a non-bone person could understand reasonably well. So that's good. You know, in biomechanics, a lot of people want to predict stress fractures, you know, in our lab and in other labs for runners. And one of the things that you showed is that you have this big variation in failure in the different bones because presumably of the bone itself and how it is structured and densities and all that type of thing. But you also showed that different types of loading, you know, cause different.
Oh, I lost Walter. Did anyone else lose
Me
Walter?
too. He's back, I think. Hey, Walter.
Hello, am I lost?
Yeah.
Sorry, I lost you there for about 2 seconds.
Okay. So my question was about going into running stress fractures.
Mm-hmm.
And you showed that, you know.
Oh no, I lost Walter
we
again. I'm very sorry, Walter.
No problem. You hear me again?
Yeah, you're back now.
Okay, let me try once more.
If you don't mind typing it, then maybe I'd be able to see. Yeah, because it's cutting in and out. So if you don't mind typing it, I'd be able to. I'll have my chat open and all.
Okay, good. I'll type it into.
Okay, I believe he's typing in. So
Maybe why he's doing that, if I just want to make some comments. So so Rob's question about duty factor is something that we've thought a lot about, and nobody's ever really done that study, and we really want to do that study because there is potential for like the material to build up some residual stress as you're cyclically loading it, and for that to kind of relax away. What we really wanted to do was kind of do it very in like an ecologically valid way, you know, where we would load it for say 2 to 4 hours or something, like a really, really long marathon run or something, and then rest it, for like a day, and then just sort of do it again like the next day and think. But some of these tests that go a million cycles, they're a week-long test for one sample. And if we add a day's rest in between this thing, now we're going to have this test it's going to take us months just to get one sample. And so we could probably do more of a scaled down version of it. We want to do it, but it's a really great point. And it's something that I'd like to do at some point in my career, but anyways, I'll let Ifaz answer Walter's question.
All right, I got Walter's question. That's a really great question, Walter. So this is my perspective on it. I think if you look at kind of the population of all young people, and you say, not everyone gets a stress fracture. Clearly, only certain people get them. And I think when you narrow it down, you see that, hey, it's the people who are doing I don't know if extreme is the right word, but they're doing a lot with their bones. They're the ones that are getting stress fracture. So in that sense, I would say that you could argue that loading is the most important thing, because without a certain amount of loading, it doesn't matter what your biology is, you're just getting nowhere near a risk of a fatigue-like failure or a stress fracture. With that said, however, I think we're starting to get a sense. I think loading and understanding loading can only get you it'll explain only so much. And I don't know exactly where we are with that. I know, for example, we maybe have a good characterization of measuring loads in people in the lab. We know pretty much how far that's going to get us, maybe. And then some people say, okay, well, to get even better prediction, maybe we need to come out of the lab and measure what people are doing in reality. And I think that's very valid. Or I think the other piece that we're missing is, fine, once we know what their loading is, let's also add information about what their bones, what their biology is actually like. So I think, so I guess if I were to answer very concisely, I'd say loading is probably the dominant thing, but I don't think it's the only thing. And I think to get, a level of accuracy. Oh, yeah, that's what I said. Okay, yeah. So now say which one is most important. I think loading is most important, because without loading, you're not going to get a stress fracture. But once you know a lot about loading, if you really want to distinguish why some people are getting them and some aren't, then I think you need to look at these other things. And that's where I think looking at the biology is really going to help us narrow things down. Especially because there's a lot of cases where you don't want to turn down the loading, because you want to be able to run, you want to be able to exercise. So being able to tell the person, hey, I'm sorry, but I know it's not fair, but you specifically probably shouldn't be doing that specifically. That would be a great thing to be able to say.
I want to join in on this.
I'm not sure if you can, I'm not sure if you can hear me now.
So far, yeah.
So far, yeah. I'm just wondering, because I know runners, when I was younger, they ran 20 or 30 kilometers a week and they had stress fractures all the time. And others that ran 200 kilometers and never had a stress fracture in their life. And presumably the loading is similarly per step, except the one person takes 6 times as many steps.
Oh, so I consider loading as the function of magnitude and duration. I consider that all in one package. So it is some relationship between magnitude and loading. And then biology, I think of as maybe being a little bit separate from that. In terms of what the combination of magnitude and duration, how that relationship is, I think the SN curves tell us something about that.
Ifaz, are you lumping biology into a person's bone quality?
Yes, I'm lumping biology into a person's bone quality.
So I think you need to be clear about that. When you say loading is important, you're saying strain. You're not saying forces.
That's right. Actually, in this context, I'm saying both. I'm saying without forces, there's no fracture, regardless of how those forces would translate into strain for a given person. So I think if I sat on my chair all day, I can have really, really tiny bones or awful bones, and I don't think I would get a stress fracture.
So you take a cross-country team of 20 people and two of them get fractured, but they live together, they eat together, they train together, they have the exact same loading profiles. One gets
among
a stress
them-
fracture out of 20. What's important, load or biology?
So now that we've narrowed down the field of like how much variability in loading there can be, what's left is now it's a difference in their bone quality. And so that's my second half of it is understanding loading only gets you so far. So understanding that these were track and field people who were together, that took us, that helped us narrow down their risk of fracture from not at all to being, okay, yeah, there is some risk of fracture here. But then to tighten that up and to be able to say who among you is going to get it, I think that distinction depends on their bone quality.
What's interesting is what's interesting to look at, we've been like searching, Bagley's doing a literature review right now, looking at stress fractures and bone quality. And if you look at, there's two types of studies. There's studies done by biomechanists and physical therapists, where they measure ground reaction forces or some other load component. And then they try to predict who has had a stress fracture or who gets a stress fracture. And when you look at that literature, it's not very impressive. You might find 50% of the studies that find load is able to distinguish those who get fractures. And then you find another 50% that don't find that. And then there's probably another 50%, if I can say that never get published because they don't find anything. And so there's publication bias.
Mm-hmm.
If you look at the studies that don't measure anything about load or training or anything, but they just measure a person's bone quality, all of a sudden you'll find 90% of studies out there will say that people that get stress fractures have lower bone mass, or they have lower bone quality, or they have thinner bones or smaller bones.
But aren't those studies inherently narrowing their field down by looking at athletes of some kind, not the general human population?
Yes, and that's what I was getting at. I was really thinking about runners, why,
Yeah.
people who run long distance, they're out there every day, and why some people get fractures all the time and others never ever do.
Yeah. So yeah, I guess, yes. So then I'll say, if you know enough information to classify broadly what a person's loading is, as in they are an athlete or they are completely sedentary, then in order to get more information about who's really at risk, I think that's when their bone quality, I think, plays a big role.
Yeah. And of course, you could argue, well, maybe they have different techniques and therefore the load they experience per step is so different that despite the fact that they do similar things and have similar biology, one will get a stress fracture because his or her technique is really lousy, whereas another person's is really good, and therefore the bone loading is not the same. So those are kind of the two extreme arguments, that the loading per step is about similar, but you have not such a good bone, or the bones are similar, but it's really the loading per step that is very different from one runner to another. You are a forefoot striker, you are a rear foot striker, you are this, you are that, and therefore the loading might be different. That's kind of what I tried to get at.
Yeah, I would like to see a much more head-to-head study that, says, here's a population. If we look at only this is how far we get. If we look, as we add more parameters, this is how much better our explanations get. I don't see that. In the absence of that, I'm kind of familiar with loosely what Brent was talking about in that. And that makes me think certainly their bone quality plays a big role. Now, Sangwon, should I answer Walter's second question or leave that?
I think you can answer the second question and then we move on to Rob's question.
Sure. So Walter's second question was, why did I define it as a stress fracture as a complete break in the experiment when that's not necessarily what happens in reality? And that's because in the experiment, it's really hard to stop at an incomplete break. So what might happen in my experiment, Walter, is if I could, maybe a specimen, I would stop it at 100,000 cycles, but instead I wind up going to 100,010. It winds up being not, in my opinion, I don't think it winds up being a very big difference calling complete fracture the failure. It's very sudden, and you can see that in our sort of force versus time or sorry, you can see that in our behavior when we look at what's happening at the peak of each cycle. It very sudden, usually it's very sudden when you can tell that the bone just broke.
Yeah, I see Rob, you have a question for Ifaz?
Yeah, I didn't get to say, Ifaz, I really enjoyed the presentation. So thank you for, again, someone who's had trouble with finite element modeling, as you know, in our previous conversations. I'm thinking about people who've had a total knee replacement, and that occurs on average in the early 60s. I think in the United States, they do about 600,000 a year. But in a total knee replacement in the 60s, you can often go from, let's exaggerate, a cowboy with legs going out like that and bending this way. But then one of the things you get with a total knee replacement is they do a complete realignment of tibia and femur, so that it now goes beautifully this way. So when one leg has been realigned, it's moving really beautifully, bending forward. And the other knee, if it was representative of what the first one used to be, is often still a bit buckled. So what you're suddenly doing overnight is you're taking a bone that's been modeled slowly over the decades as you've warped your knee a little bit, and then overnight you've realigned it. So now, fortunately it's very painful, and so you don't get out and start jogging around immediately. But I imagine that you could take the bones out of where they had been modeled and been structured in response to the forces. Now they've got completely different torsional forces until it remodels. But in people who are 60s and 70s getting knee replacement, presumably their bone remodeling is a lot slower. So is this new alignment, is that going to be dangerous? Do you think that the remodeling of the bone won't match it in time? How weak are the weak points, I guess?
The real answer is I'm not sure. I will say in terms of what loads are occurring, so I think part of the crux of your question has to do with what loads the tibia is seeing. And that's that's a situation that actually I think, in fact, in my opinion, we have a better idea of what a implanted tibia is seeing versus a not implanted one, because implanted tibias people have got measurements out of telemetric hip implants, or sorry, knee implants. In terms of comparison to what we think is happening in a model at the natural alignment and how much things shift, I'm sorry, I'm really not sure. I don't have an answer for you for that one right now, but I'll have to think about that.
But if you say that the tibia has got huge differences in shape, and you're finding these little weak points when you're getting slight amounts of torsion, the direction of those torsional forces is going to change enormously and extremely suddenly. I guess your machine, does it do testing that you could simulate that, just put it in crookedly or in a different alignment? And is it extremely weak with this alignment, but more natural in this? Because I guess mostly you try to do what would be natural, but now it's a non-natural for that shape.
So the way I would do that is basically I think of torsion as being happening in one of three axes. And so the way I would set up that test, rather than try and do a weird combination, what I would want to do is I'd want to observe how the bone behaves under the three I'm going to call them the principal directions of torsion. So twisting this way, grabbing the end, twisting this way, grabbing the end, twisting that way. And then the stress and strain distribution that's actually happening during then you know basically what's happening during any orientation of torque, because it's a superposition of those three in some form. So that's how I would approach that problem. I'm sorry, I don't know exactly what the answer is for the specific case you're talking about, but
it probably relates to what Walter was just talking about. Is it, if people have a beautiful technique and therefore it's technique that means that they never suffer a stress fracture, versus people that have perhaps a sloppy technique or poor choice of shoes, and the alignment is fine.
I could explore that with my models. Like I could expose them to different moments in different directions. And actually we did, I recently did a finite element model of a human tibia. In my case, I made the moments realistic in terms of what a healthy person is known to experience from bone pin measurements. There's nothing that says I can't play with those numbers and see how changing that would influence it. I don't know what the answer outright would be, but in my mind, I suspect there's lots you can do to make things worse. Making things better, it's hard. Yeah. So sorry, it's not a very direct answer, Rob, but that is how I would approach that problem.
Scott, did you have a last question for Ifaz?
Yeah, it's your answer to Walter's second question kind of concerned me a little bit, because if the difference between stress fracture onset and like catastrophic failure is so few cycles, that would be really bad, right? Like runners would break their legs potentially in one run, right? So do you not agree that the stress fracture probably starts to form many cycles earlier in the experiment? I don't know if that can be detected in any way with an MTS machine, but there must be some subtle sort of development. And given that we can feel pain and things, we stop loading our bones before we reach a catastrophic failure cycle.
You know what, that is true, because if I were to plot what I'd call a secant modulus across cycle, at least in some specimens, you do sort of notice a decrease before the actual failure. The problem is the pattern of that. Like some of them, like if I'm looking at it before I see an actual break, sometimes I'll look at it and be like, oh, this one's going to fail, and then it goes another 100,000 cycles. Whereas others seem perfectly fine and then they snap right away. And so I'm not actually, I'll admit, I don't know if there's a little crack in the bone during that process, because I don't really have a good way, especially if that crack isn't exactly right on the surface.
It makes me
way of checking that.
It's a bit of a tangent, but it reminds me of steel. And steel, when they're fabricating parts, they have to investigate it for imperfections and cracks and whatnot. And one of the most common methods to do that is with a magnetic field, right? And like the magnetic field being a metal that's conductive to electricity, will show, like the dipoles will change direction in the location of these micro cracks. Is there any method that anyone has proposed in a material like bone that would follow that?
You can put ultrasound through bone and you can measure speed of sound changes. I'm sorry, I'm not off the top of my head, I'm not familiar with if anyone's been able to detect speed of sound changes as a precursor to failure though. But if I was going to look at anything that's possible to do in bone, that's probably where I would look.
Yeah, I think if you could have a setup like that, it'd be really neat, and get that micro level attention. Maybe not micro, but meso level.
You
changes in stress strain relationship.
Changes of how of at least one material property is changing over time, right? So, and maybe that relates to the eventual development of the fatigue failure. It's plausible.
Yeah.
It'd be a fun experiment to run, but I don't know exactly what we would find.
Yeah, and there's a limited amount of time and money, so yeah.
Brent, did you have a question or comments for Ifaz?
Yeah, just a comment piggybacking off of Scott's question about, so sometimes we do experiments where we define failure not as catastrophic fracture, but as something like 30% stiffness degradation. We do that when we want to do something like image it before it breaks or something like that. And then we've done like, if we define it at 20% stiffness degradation, 30% stiffness degradation, even 10% stiffness degradation, and you have a bunch of bones that you've brought to failure, there's a big correlation between number of cycles at catastrophic failure and then the number of cycles at either 30% stiffness degradation, 20% stiffness degradation, or 10% stiffness degradation. Because when you're in that sort of parish regime of fatigue where you know damage is kind of the degradation of the material properties sort of degrading linearly before catastrophic failure, it's pretty predictable. I think what Ifaz is referring to when some samples don't fail after you see stiffness degradation while others do, it's a loading magnitude issue. So when we're building that SN curve, if you're at a really low load, you might see some stiffness degradation all the way up to maybe 5–10% stiffness degradation, but then it'll survive forever just because it's able to redistribute the stress or whatever it does. So we could probably get away with something like a 20% stiffness degradation or a 30% stiffness degradation failure criteria for the experiment. And my guess is we would just get very similar R square values.
Ultimately, the reason why we went with catastrophic failure is because it's something, it's hard for a reviewer to argue that that's not a meaningful endpoint. Whereas it becomes hard for us to prove, well, why is it 20%? Why is it not 30%? Why is it not 10%? And to really demonstrate that something important has happened here that justifies us stopping. And that's why that's maybe another good explanation as to why we keep going.
You have to shock and awe the reader. Yeah.
Yeah, and you know, jumping in here quickly,
Oh, poor Walter.
You can't hear me? No?
Yeah, we can now.
Okay. Yeah, it says that my internet connection is unstable. No, from a mechanical point of view, I think it's a really good criterion. I'm just thinking about if you ever want to translate that clinically, then, you know, runners have pain and can't run anymore, usually before the tibia breaks, you know, but they have a stress fracture. And so I'm might be interesting to think a little bit how that might apply clinically. Yeah,
I would hypothesize that if complete rupture is at some number of cycles, then the threshold of pain is probably consistently at some percentage of that across different people, is what I would speculate, but I don't really know for certain.
That would be a neat hypothesis.
But yeah, it's one that needs to be tested because yeah, I don't know. And that's really hard because I think different people have different perception and tolerances for pain too, right? So maybe one person needs a really big crack in order to feel like something's wrong, whereas another person's just very sensitive. Yeah.
That's true.
I know that if I think I'm about to get a migraine, I can give myself a migraine too. So there's some of that as well.
Okay, if there is no other question for Ifaz, I would like to thank Ifaz again for giving a great talk. So next week, we have the last HPL seminar for this academic term, and Mike Esposito will give a talk entitled as Effects of Midsole Cushioning Stiffness on Achilles Tendon Stretch During Running. Thanks for coming, and I'll see you all next week.